So good morning, everyone. My name is Qianqing. I'm a postdoc researcher at EPFL. And today I'm going to present you part of my PhD work, which I just finished early this year, on digital construction of mortar joint stone masonry walls. I'm from the lab Earthquake Engineering and Structural Dynamics, and this work is carried out with collaboration of CRCL lab, which is mainly a lab on robotic construction. So why we are talking about stones here? So stone is a very sustainable construction material. It has an extremely low embodied energy. However, one limit in stone construction, obvious limit is that it's really labor intensive. So here on the figure on the right, it shows the construction process of a stone masonry wall that we had in our lab. So basically, this is a process that involves a lot of skilled craftsmen, or we call them masons. So the masons select the stones, shape them, and then put them in the wall according to their experience. And this experience-based construction method results in stone masonry walls with different textures. And unfortunately, this variety of texture cause a really difficulty in structural analysis, because this texture, or we call it the microstructure, influence the structural behavior of stone masonry. And the current practice is to is in the code. For example, here is the figures obtained from the Italian code. So basically, they classify stone masonry walls according to the texture, and then when it comes to structural analysis, we assign the structure to a specific category, and then assign the material properties, all those things following. However, this process is quite subjective, and as you can imagine, it causes some ambiguity in practice. So what we do here, and what we have in what we envision, is that for every stone masonry wall that we constructed, we also build the digital twin along it. And when I say the digital twin, I mean the digitalization of the microstructure at the scale of each stone. So, and this kind of digital twin or digital model enables us for further microscale simulation and modeling and analysis for us. And we already have another project that tries to scan the stones and their position in the wall at the same time as the masons doing the construction. And as you can imagine, this process is really complicated on site, because masons are really angry that we stop them because we need to do the scanning. So in the end, we come up with the other idea that we can use robots. So the idea is to give us a bunch of stones. We scan all of them, and then we have some kind of computational method to determine where each stone should be. And then we have the robot that just execute this design as precisely as we want. And then in the end, this gives us a digitalized micro scale model of the wall. And this is the pipeline that I will describe in detail in the following. So, at the start of the project, we need to first know where each stone should be for the robot. And for this, we develop a computational design method, or we call it a stone stacking algorithm, that mimics the behavior of masons in stacking stones in a virtual environment. And to develop such method, we draw some masonry rules from practice, such as masons normally, they don't put stones with the joints aligned, and they always shift the joints to form a little bit of a interlocking, we call it. And these are kind of the rules we formulated into an optimization problem, and then we solve it with a technical discrete convolution, and in the end we achieve an optimization efficiency of 4 seconds per stone. So it takes us 4 seconds to determine where this stone should be. So once we have it, we give this plan to the robot, and then it can execute. And here are two construction experiments that we carried out. First one on the smaller scale, and then next one on the larger scale. And if I can play this. So here we're using an ABB robot. So basically the idea is the robot, we have a suction-based an effector that it takes the stone and put the stone in a place where our computational method suggests. And then we go to, we construct another stone masonry wall with around half a meter scale with the stones ranging from 10 centimeter to 40 centimeters. And in this process, as you can imagine, stones, they are a little bit, I mean, once the robot places it, it could move a little bit. And this caused, if we let this error accumulate, as you can imagine, that in the end, the constructed wall will be quite a little bit more different than what we planned. So we incorporate a digital twinning process that every time the robot places a stone, actually place one layer of stones, we scan this wall and then register stones from their planned position to the as-built position, and then use the as-built positions to feed the planning algorithm and all the following. So in this way, we have a closed loop construction process for every layer of stones. So here is the result. This is the wall of around half meter size that we built in the lab. And here in the middle is the surface model that we obtained in the last round of construction. And on the right is the digitalized microstructure with stones in blue, showing where they should be in the planning, but in green in the final as-built position. As you can see, there is a little bit difference, and then the maximum tolerance we have is 4 centimeters, and with most of the stones fall within the placement tolerance within 2 centimeters. So as a conclusion in this work, we introduced a pipeline for digital construction of stone masonry walls leveraging robotic construction. And then this micro-scale digital twin is created at the same time of the robotic construction. And this enables us for a more precise robotic assembly. And also the digital model that we obtained can enable us for a micro-scale simulation, which can predicts much accurately and precisely the behavior of the wall that we constructed. And here are some simulation works that we're doing right now, how we use these digitalized micro models for simulation. And with this, I would like to conclude my presentation, and thank you very much for listening.